SwayamPrabha. Digital India. Educated India.
So, welcome to lecture 6, okay. And so let me show you the book also that you are going to follow. So, this is the book by Transport Phenomena in Multiphase Systems by Amir Fagli and Yuan Zhang, and the other book will be when we go to the droplet combustion and evaporation part, we will use Bill Shiriniano's book. I will show that in due course. But this is the book which you should normally follow. Okay. So, let us look at now in this particular lecture microscale vapor bubbles and liquid droplets. The full fledged study of vapor bubbles and liquid droplets will be done later on during the course. But this is just the initial idea of what it is, right. So, let us consider a situation that you have an isolated rigid system. Rigid system means the volume won't change, right. So, it is like a rigid vessel. Okay. And inside this vessel you have this vapor bubble. Okay. So, there is liquid here, this container is filled with liquid. The liquid has got a pressure of PL, temperature TL. This is the interface, and we covered a lot about interface, just a few in this last few lectures. This is PV and TV. Okay. These are the corresponding pressure and temperature within the vapor bubble, right. Okay. Now, so this is the situation, right. So, you have an isolated, it is like it is an enclosed cavity in which it is you have filled it with water. This vapor bubble forms due to whatever reasons, it could be due to boiling, due to extra heat, but we have this vapor bubble which is at a temperature of TV, pressure of PV. We have the liquid temperature of TL and pressure of PL, and then there is a interface. Okay. Now, from the calculations or the things that we showed earlier, this TV is equal to TL is equal to TI, right, that we did just a few lectures back, is not that so? And we also said mu L is equal to mu V equal to mu I. Right. What it means is that the temperature across all the phases are the same, right, TV, TL and TI, they are the same. That is, the interface temperature is the same as the vapor temperature, same as the liquid temperature. Also, we have also said that the chemical potential is the same across the two phases, and that chemical potential is the same as in the interface as well. Okay. So, this is a vapor bubble, this is the condition that we got from our thermodynamics that we did in the last few lectures. Okay. So, the vapor at temperature TV and pressure PV is a microscale spherical bubble with a radius of RB. Let us put this radius as RB. So, if you take the bubble out, this is the radius RB of the bubble, right. So, it is basically what? It is a microscale spherical bubble of radius RB, correct, right. Okay. The liquid temperature is also at a constant temperature of TL around the bubble, right. So, this part is quite clear. Now, let us apply the Helmholtz free energy function on this. Okay. So, what is that? For the liquid, let us write we are just retaining mu over here because of this particular relation, right. The mu is the same, okay. So, you can put it as mu for example, okay. Similarly, dFV, that is the one is for the liquid, one is for the vapor, right. So, now that is given as sorry, I wrote the got it, that is for the vapor phase. Similarly, we can write the same equation for the interface also. Though it is the same, right. Got it. So, these are the three relationships that we can write from the three expressions, right. One for the liquid, one for the vapor, one for the interface. And all of these equations we have done like previously. So, now we are applying it to this micro scale vapor bubble bubble in a liquid pool, right, where the liquid temperature is kept constant at TL, right. Okay. Now, let us go to the next slide. Okay. For reversible process, phase change under constant volume and temperature. Okay. This dF is equal to dFL plus dFV plus dFi is equal to 0, right, as the change of Helmholtz free energy is actually equal to 0 in such a case, right. Now, so now let us, now we already know, if you go to the previous page, we already saw the individual relations, right. Okay. Now, let us add all of these things together, right. So, when we add all these things together, SL plus SV dt minus PL dVL, sorry, dVL plus PV dV plus sigma dA plus mu dNL plus dNV plus dNi is equal to 0, right. Now, the total volume is fixed, that is what we said, right. It is a rigid vessel, right. The total volume is fixed. So, dV is equal to dVL plus dVB has to be equal to 0, right, because total volume is fixed. All right. From mass conservation, what we can say is that dN, that is the rate of change of the change in moles, dNL plus dNV plus dNi is equal to 0, right. So, what we can do is that we can take and substitute it here, we can take this and substitute it there, right, because this part will become equal to 0, that you can readily see, right. dV part also, okay, we can substitute, now that you know the relationship between the two, we can substitute them in this equation and try to see what we get out of it, okay. And also, since phase change happens at constant t, right. Okay. So, therefore, this implies that your dt has to be equal to 0. So, this term also goes to 0. So, essentially after substituting all of that, you become PV minus PL is equal to sigma dA by dVB, right. Okay. Now, we already know if it, since it is a spherical bubble, area is nothing but 4 pi RB square. The volume of the bubble is basically 4 pi RB cube divided by 3, right. Okay. If you substitute them back, that means dA will be equal to 8 pi RB, right, got it. So, dVB will be equal to, so 4/3, that means 12 by 3 pi RB square, correct. Okay. So, this is becomes basically 4. So, now dA by dVB will be equal to 8 pi RB divided by, sorry, let us write this once again, 8 pi RB divided by 4 pi RB square, right. So, this basically gives us 2 divided by RB, right. So, therefore, PV minus PL becomes 2 sigma by RB, which is basically also called the Young Laplace equation, right. So, clear what we did is for reversible phase change occurring under constant volume and temperature, the sum total of the Helmholtz change of Helmholtz free energy has to be equal to 0. This we know from the previous cases when we were studying equilibrium of the systems. Okay. Similarly, using this, if we sum total all the Helmholtz free energy quantities, that means these and these, we get a term like this. We apply additional constraint like the total volume is fixed, we apply the mass conservation, that means there is no net change in the number of moles, and phase change we have also said that it happens at a constant t. Using all that and using the definition of the volume and the area of the bubble, right, we have calculated that the pressure inside the bubble, that is PV, okay, and the pressure outside the bubble, which is the pressure of the liquid, okay, is basically given by this particular quantity. Okay. So, that means the pressure inside the bubble is actually more than the pressure outside the bubble, that means the liquid pressure, right, because it maintains a convex shape. Okay. So, RB and everything is positive basically. So, we can say that the pressure inside the vapor pressure inside the bubble has to be more than the pressure inside the liquid, right, and this is what happens when a bubble is actually stable inside a pool of liquid, right. So, let us look at, now that we have done that, let us look at a few more alternative type of definitions. So, at phase equilibrium, the chemical potentials are the same that we already established, right, for both phases are same. Right. Okay. So, we can say the Gibbs free energy they are the same, right, okay, for pressure and temperature, whatever, I mean the Gibbs free energy has to be specified. So, if we differentiate, we get dGL by dPL dPV. Okay. Now, if you recall a little bit of your earlier work, your volume for S comma Ni the same as your dG dPV T, rather not dPV, but let's just put it as okay, right. So, that is the definition. Okay. From the Maxwell relationships you can work out that. Okay. Now, using this you have VL dPL is equal to VB dPV. Also we just now saw PV minus PL is equal to 2 sigma by RB, right, that we just now proved. So, dPV minus dPL is equal to 2 sigma by RB square dRB. Okay. So, if we eliminate pressure in the vapor phase, this becomes VL, or if we try to eliminate, it is not yet eliminated, 2 sigma by RB square dRB equal to VB dPV. Now, for an ideal gas, vapors in most cases can be taken as ideal gas. For ideal gas, RGT divided by PV. Okay. So, you put that expression for VB over here, we get RGT dPV by PV minus VL dPV to 2 sigma, this is sigma, by RB square VL dRB. Now, if the radius of the bubble goes to infinity, very, very large bubble, okay. So, the radius of the bubble goes to infinity. That means 1 by RB should approach basically 0, right. So, and PV is the same as the saturation pressure, right, because we have taken it is an equilibrium process, there is no superheating or subcooling or anything like that. So, this equation that we have over here, if you look at this particular equation, this particular equation can be integrated, okay, can be integrated, and we can get RGT ln PV by Psat minus VL PV minus Psat equal to minus 2 sigma by RB VL. That is what you can get. Now, if you cast it, if you take out all these things, so that PV will be equal to Psat into exponential VL PV minus Psat minus 2 sigma by RB divided by RGT, close the bracket. This shows that this bubble is in equilibrium. A bubble can be in equilibrium if only if and only if PV is greater than Psat, right. So, the vapor pressure that is inside the bubble, right, has to be more than the saturation pressure. In other words, the vapor should be kind of superheated, right, must be superheated. Got it? So, that is comes from the thermodynamics, got it. So, the vapor must be superheated because this expression shows that it has to be greater than the P saturation pressure. Okay. So, this is an important for a bubble to be stable, this PV has to be more than whatever is the saturation pressure because of this temperature, this TV, Ti and TL, right. Okay. So, it has to be in that same particular form, got it. Okay. So, what we have learnt over here is that we have taken the surface tension analogy, right. We have taken the surface tension and we have found out what interfacial behavior is. We have applied the same over here and we have been able to show two key relationships. One is the Young Laplace equation, which shows that the vapor pressure inside the bubble is more than the liquid pressure, right, that is the first thing. And second thing that we have shown, just by following similar type of thermodynamic analysis, we have shown that this vapor pressure has to be more than the saturation pressure, okay, at that temperature whatever at which this phenomena is happening, because the temperatures are all Ti is equal to TL is equal to TV, right, that we know already from a thermodynamic equilibrium relationship, right. Okay. So, this actually shows that this almost completes the thermodynamic section. Let us look at the presentation once again. So, what we will do in the next class is basically go and solve for the generalized governing equations in the multiphase flow. So far what we have done? So far we have done is that we have looked into the individual thermodynamic relationships that connects to multiphases, multi-components. We have looked at the surface tension behavior, which is the most important thing. We have looked at interfacial, when there is an interface present, what happens to the chemical potential, to the temperature. We have also shown a little bit that the liquid and the vapors can be superheated, subcooled, etc., and that need not be, that is not a deal breaker per se. Okay. So, now that we have covered the thermodynamics aspect of it, in the subsequent lecture that we are going to give, okay, we are going to cover the generalized governing equations in the multiphase flow, right, because the generalized governing equations are the equations which basically tells you that how transport happens. So far we have not taken into account any transport over here. We have just looked at the thermodynamic principles, okay, that what is non-PV work, what is PV work and things like that, right. So, just to close this lecture, so let me give you just a brief recap. What we have done is that we have looked into the first law and the second law of thermodynamics essentially for a closed system, okay. Then we have gone through Gibbs phase rule, right, because Gibbs phase rule is something that gives you that what is the degree of freedom of a system. Okay. We have also looked into the equilibrium and the stability of single phase closed systems, and this is where you get that the different principles, that the change in Helmholtz energy has to be less than equal to 0 and things like that. Okay. Then we have looked into the Maxwell's relationships, which is one of the most important part of the thing. Okay. You are also suggested to study about the thermal, mechanical stability and chemical stability. There are 3 types of stabilities, okay, but that you can read from your undergraduate book, which actually shows that what are the 3 stabilities and what are the requirements to fulfill those things. Okay. We have also looked into system with compositional changes, but having a single phase. Okay. So, that means it is a multi-component system. We have looked into systems which has got 2 phases and what are the criteria, and we have seen that temperature, pressure and the chemical potential has to be the same. Okay. We have also looked into the Clausius-Clapeyron equation and the Clapeyron equation only. Then we have looked into the thermodynamics of the interfaces, that means what will happen when you actually have an interface into the picture, and then subsequently we have looked into the definition of surface tension, and we have given as many as 3 definitions of surface tension. okay, with respect to energy, with respect to Gibbs free energy, with respect to Helmholtz free energy, okay, and we have shown that what surface tension is all about. Then we have studied the liquid vapor spinodial curves, that means basically the metastable equilibrium conditions. Okay. We have also looked into the multi-phase multi-component systems, that means when there are two components and two phases present, what are the equilibrium conditions. Okay. And we have also looked into the superheat limit, that means we have already established that liquid and vapor spinodals actually do exist. So, why not look at the superheat limit for the same. So, and apart from that we have done this microscale bubble and liquid droplet analysis to show that what is the stability criteria, or how, what will be the pressure inside a vapor bubble, okay. And the same can be done for the liquid also. So, it is not a big thing, okay. So, that is what we have done through the course of these few lectures. So, in the next lecture we are going to start with the generalized governing equations in multiphase systems, okay. So, that will be next.